All right, so today we are going to focus on the manipulation techniques of the Maclaurin series that we came up with yesterday. We came up with 3 Maclaurin series. We came up with e to the x, sine of x, and cosine of x. Yes. And we actually did one of the manipulation techniques already on one of the problems. But the whole idea behind this is that because we have something that is an equivalent statement, and I can say that my series my function equals the series, when I actually go through and I were to do any of these manipulation techniques, essentially what I'd be doing is I'd be saying, well, if I substitute in a value here to here, then I could also sub in the value on the other side of the equal sign, and that would work. Anytime something is equivalent over an equal sign, we find out that the Maclaurin series for these 3 things winds up being the same exact conceptual type of problem. For instance, one of the things we can do is we can substitute into a Maclaurin series to be able to get a new series. What do I mean by that? Well, let's say I was looking at f of x is equal to sine of x squared. If I were to come up with the Maclaurin series, first off, we would have a small problem, because every single one of these terms would wind up with a 2x, and after the first one, we'd actually wind up having to do a product rule built into that, and it gets really gross really fast. Trust me, you don't want to do it. It's just not cool. On top of that, if I were to ask you to integrate that question, you wouldn't be able to do it because the sine of x squared doesn't have any antiderivative. But one of the things I can do is I can actually take, let's say, I know, well, if I'm looking for the sine of x squared, well, I know what the sine of x is. Is sine going to be the odd or the even series? It's the odd series. So we would have x minus x to the third over 3 factorial, and we're just going to use odd powers and odd factorials as we alternate. And we had the general term -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. And that's an equivalent statement. This is the same exact thing when we're looking at these. Well, if I wanted to find f of x, which we're going to call the sine of x squared, what I can actually do is I can simply take all of the x's and turn them into x squareds. And by turning all of the x squareds into factorials, or all the x's into x squareds, not factorials, I don't know what I was saying there, but by turning all of the x's into x squareds, by substituting out that value, I can create a new series off of the old one, where we would have a general term now of -1 to the n. I tell you what, I'm going to actually substitute in my x. So I actually will have x squared. This is actually x to the 6th. This is actually x to the 10th. This is actually x to the 14th. So I've got 2, 6, 10, 14. What is my new x power going to be? It wouldn't be 2n this time, because 2n would give me 0, 2, 4, 6, 8, 10. Almost. 4n plus 2 would work. Yeah, that would work. Over. By the way, for those of you who are curious, if I would have done a direct substitution here and called that x squared to the 2n plus 1, wouldn't we multiply those together anyways? We would multiply the 2n plus 1 times the 2. That would give us our 4n plus 2. So we could literally do a substitution even into the generic term if we felt the strange desire to do so. So one of the things I can do is I can literally do a substitution into my series to come up with a new series without having to do any extra work. Sure, why not? Sounds like fun. Another thing we can do is I can differentiate the series. Like I said, when I did the cosine manipulation, that's exactly what I did. I actually took the derivative of sine to get to cosine, and then I took the derivative of the series to get to the answer. Well, one of the things I'm allowed to do is if I want to find f prime of x, maybe I really don't want to actually have to take the derivative of sine of x squared for some really bizarre reason. I don't know why we don't want to do it. We just don't want to now. One of the things I can do, though, is if I took the derivative of that, that would be what? 2x cosine of x squared, something weird like that. Well, 2x cosine of x squared, we could do some substitutions with that too. But instead of doing that, we could actually take this, and instead of calling this x squared, we can call this 2x. Instead of calling this x to the 6 over 3 factorial, that would become 6x to the 5th over 3 factorial. Instead of calling the next term x to the 10 over 5 factorial, that would become 10x to the 9th over the next term. Yeah. Now, we could theoretically reduce that, but I don't really want to deal with it, so I'm not going to. So the question was, could we, the bottom would stay the same. 6 over 3, I could reduce that. I could call that 3 over 2 factorial. I could call this 2 over 4 factorial. I could call this 2 over 7 factorial, or 2 over 6 factorial. My apologies. Which would be kind of cool. We can actually talk about that in just a minute. Negative 1 to the n. What on earth is this going to be? First off, I've got to deal with this 2, 6, 10, and 14. So how to get 2, 6, 10, 14? What do you mean? Sure. Four n minus 2. I like it. We could call it that. What would you be counting from if you did 4n minus 2? That would be letting n start at 1. Now, in the last problem, we started at 0. So we probably want to start at 0. And I'll talk about that in just a second. I personally would call this 4n plus 2. And I'll talk about something in just a second. Yeah, it's going to be 4n, not 2n, because we want to increase by 4 each time, right? What is our x going to be? Well, really, this is just one less than the previous one, than the coefficient, right? So could we call that 4n plus 1? Now, I just want to bring up a point because you said something that's interesting. This and this oh boy, I've got to think about this one now. Hold on. 4n minus 3. And then, oh man, that'd be 2, become 2n minus 1. Same outcome. This is n at n, come on. All right, I'll stop. This is n starts at 0. This is n starts at 1. These two are the exact same thing. They're going to give you the same exact set of numbers. It just depends on where I start my n at, because if I start my n at 0, I need this to be negative 1 to the 0, which would give us a positive number on my first term, agreed? So I got a positive number. 4n plus 2, I would need to get 0 plus 2 to get that 2 value. 0 plus 1 would have given me my 1 value, and 0 plus 1 would have given me my 1 factorial. Agreed with that? However, let's say I didn't want to start in at 0. Let's say I want to start in at 1. If I would have plugged in a 1 into this, that would have given me a negative 1, and that's not what I have. So I would have had to have reduced this by 1 to get to that value. See what we're saying there? So then if I plugged in a 1 here, I would have 4n minus 2. Well, 4 minus 2 is 2. 4 minus 3 would give me my 1, and 2 minus 1 would have given me my 1 factorial. So this gets really weird. This is going to be the thing that's really annoying, is that you could come up with a solution for a general term, all right? And Andy and Trin could be comparing their answers. And their answers could look completely different, because you don't have to tell somebody where you're going to start from. You can just write your answer down. And Trin may have started at 0, and Andy may have decided to start at 1. And their answers look completely different, and they have to recognize that they're the equivalent answers. They just started at different locations. Now, I have a favorite starting point. I really like 0. I'm usually going to stick with 0 unless 0 makes my life a whole lot harder. Very rarely will I use something that's not 0, although when I was doing one of the assignments today, as I was going through, for some reason, one of the problems I started at 1, and I couldn't even tell you why I did it. So be aware of that you're going to have to deal with that at some point. It's not terrible, it's not bad, it's just, and most of the time most people choose to start at 0, because that's when we come up with an equation for slope-intercept form. We start when x is 0, so it makes a lot of sense, and we want to take that particular piece of information with us. Cool? Now, from this point on, I'm not going to start at 1 anymore for the rest of the day, because I really don't like starting at 1. It's weird. Some of you are like, I don't like starting at 0. What on earth is all of that? I don't know. I'm going to erase it. It's answers. All right. So that was the first thing, is that was actually manipulation technique number 4. We can take a derivative or an integral of something. We're going to integrate again here in just a second. Another thing we can do is we can multiply by a constant or a variable across the problem. So if I have the cosine of x, all right, cosine is the even problem, so that means that we would have even coefficients, or even powers, even n values. X to the 4 over 4 factorial minus x to the 6 over 6 factorial plus negative 1 to the n, x to the 2n over 2n factorial. So if I have the cosine of x, which is 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, negative 1 to the n, x to the 2n over 2n factorial. That's what I have. I want to find f of x, which in this particular problem is going to become x times the cosine of x. Well, if I multiply one side of an equal sign by x, I would have to multiply, ladies and gentlemen, the 1 will become an x. This becomes x to the 3rd over 2, x to the 5th over 4 factorial, minus x to the 7th over 6 factorial. Negative 1 to the n, x to the something. What is the x to the something? 2n plus 1? Makes sense. We just added 1x to that, didn't we? All over 2n factorial. Ladies and gentlemen, you can multiply by x. Probably the most important application, one of the most important applications for these power series, though, lies in the next example. You can take a derivative, but derivatives typically aren't very hard. You know, you get some product, quotient, power, you know, all that stuff, but overall, they're not necessarily difficult. We have an issue with integration, and in this problem, this actually isn't, this is something that I would probably have still integrated, because I can take the integral of x cosine of x. What method would you have to use for x cosine of x? If I u sub that, I would choose x, and then I get u cosine of u, which looks a lot like x cosine of x. Product rule is a derivative. This is an integration by parts question, which isn't necessarily fun, but it's not as bad as what we're going to do. With that said, in the previous question, where I was looking at cosine of x squared, this is actually a problem that I would have to use a series to come up with an integral for. But we'll get to that in just a minute. So let's say I wanted to integrate, okay? So now I'm going to integrate with respect to x, my f of t dt. F of x was x cosine of x, so f of t will be t cosine of t, which is t minus t cubed over 2 plus t to the 5th over 4 factorial minus t to the 7th over 6 factorial plus some dots. Now please notice that I did change all of the x's into t's. That is important. Remember that the variable as your limit cannot be your variable in your problem. All right, now I would have to take the antiderivative of this. What is the antiderivative of t? T squared over 2. What is the antiderivative of t cubed over 2? T to the 4th over 4 times 2? You could call it 8. I'm not going to, because the next term would be terrible. Oh, what is 4 times 2? No, we're going to leave it as 4 times 2. What's the next term? T to the 6 over 6 times 4 factorial. And this is where I choose not to multiply that because, oh my goodness, that would be terrible. The next term is minus t to the 8 over 8 times 6 factorial. This is getting really dumb really fast. Plus a bunch of dots. Evaluated from 0 to x. Now, here's the next thing that I want to point out. I'm going to look at this series at x, and I'm going to look at this series at 0, and I'm going to do the series at x minus the series at 0. I can actually add and subtract series. I can actually take an infinite number of terms and add the infinite number of terms to another infinite number of terms to get a different series of an infinite number of terms. What? Now, here's the cool part. Let's do the x values. This is really just x squared over 2 minus x to the 4th over 4 times 2 plus x to the 6th over 6 times 4 factorial minus x to the 8th over 8 times 6 factorial plus, if I evaluate this at 0, what's that going to be? 0. All the t's become 0. There's a t in everything, so the whole thing becomes 0. So I am actually ready for my general term. X to the what? What do you want to call it? Okay, I'm going to call it, and that's what I would personally call it. I would call this x to the 2n plus 2. There are some people at this point that would probably call that x to the 2n, but we'd have to stop and think about that. If I called that x to the 2n, what did I start at? I started at 1, and then I got to modify everything else. So I could call this negative 1 to the n, x to the 2n plus 2, over two n plus 2 times 2n factorial. Now, interesting thing, if I actually looked at my term here, when you take an integral, what do? You increase the power by 2n plus 2, and then you divide by your new power, 2n plus 2. all sorts of crazy. But now again, this particular problem is not necessarily the best one to look at for this. But when I go through and I should have actually taken the antiderivative of that just so you can see how that pans out. Maybe I will in a couple of minutes just to show you. But when you go through this and we multiply that all out, that winds up becoming this nastiness. It's kind of crazy. It's kind of weird. Sound good? All right, then here's what I'd like you to do. I'd like you to pull out your pink packet. I do not have a copy of it on my board, so I'm going to have to do this a little bit old school here. But if you will pull out your pink packet, I want to help you out through some of the first things because this is kind of weird. And I want to make sure you understand what we're trying to get to. Yes, the 5 through 8 questions are all from the notes from today, which will probably make a whole lot more sense if you were trying to do those the hard way. That was probably terrible and miserable, and you probably wanted to awesome, and then suddenly poking your eye with the salty French fry sounded like a good idea. It's something unpleasant. It's not like it's permanently maiming, but there are some questions that you do that seems like a better choice. I understand. I have been there. I have felt the pain of some of these questions and then watched somebody go, oh, all you had to do was, and you go, oh, it's all good. Well, no, and number 1 is long and it's weird, and I want to make sure that you understand what I want to do from this. Okay, so what I want to do, the concept of a power series has existed before the concept of a Taylor series. All right? The idea of a constant times x minus a center to a power, depending on what term we're on, that concept existed well before the concept of the Taylor series. And what Taylor wound up doing is saying, hey, we can make these special series off of other functions so that we could manipulate some harder to deal with functions into polynomials that we can deal with. All right? So that's what Taylor did. What I want to do today is kind of show you a derivation of how we can go from a power series and from a power series actually get the values of A, so A0, A1, A2, A3, and actually figure out what that coefficient is for a Taylor series. Because when we talked about Taylor series, we said, well, A of 0 is really just f of c, right? A of 1 was f prime of c. This was f double prime of c over 2. F triple prime of c over 3 factorial. F to the nth derivative over n factorial eventually, right? So if I were to look at this particular problem, we have f of x, right? Is all of this. This is your power series. What I'd really like to do is I'd like to figure out what on earth does a of 0 equal, right? So if I want to figure out what a of 0 is equal to, I need to get rid of a1 of x minus c, a2 of x minus c squared, a3 of x minus c cubed, a4 of x minus c to the fourth, a5 to x minus c of the fifth. I need to get rid of every single term except for a of 0. The only thing I can manipulate is the x. How do I make every single term disappear except for the a of 0? Ooh, not make x 0. Because if x is 0, then this becomes negative c squared, negative c cubed, negative c to the fourth. What can I do to make every single term in this problem except for a0 vanish? Make x to c. If x becomes c, then every single x minus c becomes 0, right? Well, let's do that. If we look at f of c, then all we have left is a of 0. Agreed? Well, if f of c equals a of 0, then a of 0 must equal f of c. I know, it seems like a dumb statement to make, but it's something that we have to do. That seems really dumb, but okay. I promise it will eventually become something interesting. Was that bad? Now, here's the deal. I want to get away from a of 0. I really want to find a of 1. But if I'm looking at this equation as it's written, there's no way to get, whoa, that was cool. I didn't even touch the board. If I wanted to go here, I couldn't really find a way to make this term stick because I would still have all those other terms, right? I need to come up with a way that I could drop this a of 0 ideally, and I'd really like to just get to the a of 1. And it's not as obvious of work, but one of the things I can do is what if I were to take the derivative of f of x? Well, the derivative of a of 0 is 0, it's gone. What's the derivative of a1 times x minus c? It would be a1 times x minus c to the 0 times 1, because there's a chain rule built into that. But if I do a1 times x minus c to the 0, x minus c to the 0 is just 1, so this suddenly becomes a1. The derivative of a2 x minus c squared is 2a2 x minus c to the 1. Agreed? The derivative of the next term is going to be what? 3a3 x minus c squared. Derivative of the next term? X minus c to the third, 5a5, start getting into a pattern eventually, to the fourth, plus, ooh, okay, now we got a general term. What's the general term going to be? In a sub n of x minus c to the what? There it is. Nice. Again, my goal is to figure out what on earth is a of 1. What can I do to find a of 1? I'll make all the x of c again, right? And instead of evaluating f of c, I can evaluate f prime of c, which will give me a1, which means that a1 is, okay, I promise, we're going to get something interesting there eventually. It does make sense, but this is kind of dumb. It's okay, I'm about ready to make it not dumb. Okay, so then the next step is we want to find a2. Well, since the process worked last time, take the derivative and evaluate at c. Let's take the second derivative of this term now. So now a1 goes to 0. This becomes what? This is 2 times 1 times a2 x minus c to the 0, right? What's 2 times 1? What's another way I can write 2 times 1? 2 factorial. Plus, what's that going to be? Don't say 6. This would technically be 3 times 2 a sub 3 of x minus c. Your next term is going to be 4 times 3 a sub 4 x minus c squared plus 5 times 4 a sub 5 x minus c to the third. What is your nth term now? N times n minus 1 a sub n times x minus c. You're 100% right. Times n minus 2 to the n minus 2. Wow, that got really weird. But what happens if I evaluate f double prime at c now? Now what do I get? I get 2 factorial a sub 2, which means a sub 2 is what? F double prime of c, ladies and gentlemen. Do the third derivative part, come up with the general term, and then input your information that you got earlier. That should give you at least a starting spot for this particular question. Have fun, enjoy. You got the rest of the time to work on stuff.